Great, thanks guys. And our last talk for the session this afternoon is Kyle Kreitz on DNSFlow.
All right, good afternoon, everyone. My name is Joe Eggleston from Deep Field Networks, and myself and Kyle are actually going to be both talking about DNSFlow. So I'm first going to be giving just a brief introduction, motivation, and then Kyle's going to talk about how he has been using DNSFlow within Merit's network. I just wanted to start out by going on record as saying that I, for one, welcome our ITU overlords. And so I thought it would be useful maybe to start with an analogy to telecom networks. Mostly I think this analogy is useful because it kind of helps illustrate how this how DNSFlow can be powerful and useful within the internet, within an IP network. So within telecom networks, they have this concept of data plane, or different planes that the network is built on, the data plane, the control plane, and the management plane. And this doesn't exactly completely apply to an IP network. Within an IP, it's in some ways, I guess I would argue, a lot simpler. Other people maybe would say it's more messy. But basically, if you want to understand what's going on within the data plane, within a telecom network, it's really useful to look at the control plane, because that is what gives you the, when a user is dialing the phone, the control plane is what's setting up the network and setting up the call. So the control plane informs you about what's going on within the data plane itself. And can you do the same thing within an IP network? Well, I think that you could argue that DNS is the closest thing to a signaling plane or control plane within an IP network. It's how the user expresses their intent. Right now, if we want to understand what's going on in the data plane, we have to use something like NetFlow or its friends. And these are incredibly useful, but they have their limits. I think you get a real power by combining DNS, so the signaling from the user, with the telemetry coming from the routers. And by combining these two things together, you get a whole new world of information that before wasn't possible. All right, so DNSFlow, what is it? Basically, it's a protocol and reference implementation for the efficient export of DNS telemetry. To be clear, the thing that we're mostly interested in is the recursive responses. So this is sitting south of the recursive resolver. And there is related work, for example, like the ISE, passive DNS work, which primarily uses iterative responses. For us, we think that the main operational benefit actually comes from looking at the recursive responses. And the goal from DNSFlow, the thing I'm most interested in, is getting open access to this data. And so the problem right now is that there's not really any easy way to get access to these recursive responses. You can enable, I guess I don't want to go quite yet. You can enable syslog on a router, or I'm sorry, syslog on a DNS server, but that will pretty much crush the server. And beyond that, there's not really any open, standardized way to get this information out. So the first challenge or the first issue that most people come up with is the scale of the data. And I think we have a pretty good answer for this. And Kyle, actually, some of the results he has illustrates it even better, that the data is incredibly redundant. So it's really easy to come up with cheap and easy ways to compress this. You can, right off the bat, I mean, users are doing the same thing over and over and over again. You only have to see www.google.com so many times before you know, or you can come up with a way to compress that really easily. So you can get 1 to 20 compression ratios based on the data we have, and with just a little bit more cleverness, you can go even further. All right, so our status, we're cool, so we're on GitHub. You can join us there if you're interested. You can download the initial version right now and play with it. It's really simple, a couple hundred lines of ANSI C. It has flow-like output. The upcoming version will be using IPFix just to make it easy to interoperate with the current set of tools. We'll have support for the compression and sampling built in, and it's currently deployed in several production networks. Just in case it wasn't clear from before, we're talking about deploying this. It is either, you could do it on a recursive resolver itself, and we have some ongoing discussions with some of the commercial DNS servers about implementing a plugin for those servers, or if you have a span or mirror port that can grab this traffic and send it to a VM in your cloud or commodity PC, you could run the code there. Oops. Okay, yep, and with that, I will turn it over to Kyle.
So I'm going to briefly talk about a simple operational thing that you can do with the data. So first thing that we tried to do is come up with something that was useful to people who are running networks. And as you run a network, if you run your own recursive resolver, you sit between your customers and that resolver, and you can help them by using these blacklists to identify phishing activity. If you're recording all of the responses from your resolver, you can throw that into a database, which we did, and then run nightly queries to report which clients were phished and by which domains, and you can automate this to do a run nightly. So let's talk about the data itself. We wanted to characterize DNS to IP mappings as we observed them. There are two basic types of entries that we found, largely dynamic mappings, meaning things that change frequently or had many named IP mappings, and then largely static name IP mappings that didn't change across the period of observation, which was 3 weeks. After the first 7 days, the rate of growth flattened out quite a bit, as you can see in the graph, and it approaches roughly constant. There's a small diurnal shift, but so again, 2 major contributors, 5 TLDs account for 90% of the data, 308 TLDs. So there are very few domains that have a large number of named IP mappings. The 20 largest have 43% of all of the pairs, although 98% of the domains, the second level domains that we examined, had fewer than 20 named IP pairs. So I guess in summary, very few have a really large number of named IP mappings, also meaning that very few were extremely dynamic, but the ones that were very dynamic. The top 8 had 10,000 entries each. And so now what we did was we looked at the distribution of unique IPs across the set of name IP mappings. So we just pointed out a couple of large dynamic services. Where there's a pointer. So you can see CloudFront right here has about about 80,000 name IP or IPs. No, it's 8,000, isn't it? I'm sorry. And then the last thing we did was looked at name IP pairs and classed the into name and IP pairs. So across each /8, how many name IP mappings did it have in that /8? So you can see that CloudFront is a major contributor with around 52,000 name IP mappings and a couple of other fairly well-known services. So that's all of the data that I have to go through. Does anybody have any questions about our data or implementation? All right, well, thank you very much.
Thanks.
All right, thanks very much, folks. That about does it for the session. Just a quick reminder, we do have a break now, and then not long after that, there is the DNS track, which is in, I believe, also in here, in the ballroom, starting at 4:30. And don't forget, there's also a social tonight, 7 o'clock, at the TELUS World of Science. Thanks very much. Oh, and please fill out your surveys. Thank you.